Okay, good afternoon, everyone. Thank you for the opportunity for me to share this work that was done recently with my student, Jaykumar, Patel. As the title shows, it's just a typical application using machine learning or deep learning for an interesting application. Okay, it's for classifying galaxy images. Typical table of contents, they give you introduction, some background, literature review, and all that. And we conduct some experiments. We try to show our results is a little bit better than some of the existing work. So very typical table of contents. So we don't have the luxury these days to see the stars anymore, especially in big cities. The light pollution is so bad that we hardly go out to enjoy the light sky. But if you go to a dark area, there are many dark parks in Canada, US, just a very remote area, you can go there, you look at the star, it's beautiful. So astronomers, they have developed a way to kind of classify the galaxy, the images. We sometimes see a bright spot or dot. In fact, that's a galaxy, eh? It's just so far away. We thought it's just a planet or star, but it's in fact a galaxy. And Edwin Hubble initially developed a way to visually inspect the image of the galaxy to classify it into different categories. And that's just image shows a typical classification system used by astronomers. Unfortunately, none of us here, I suppose, are in astronomy, so we know very little about the significance of this. The astronomers tells us it is very important for them to know what shape this galaxy looks like, because this tells them and us the evolution of that galaxy, how that galaxy was formed, and it may even tell us the chemical and the physical property of that galaxy. So it's very important for them to know the morphology, that's what they call it. To me, it's just, to our normal person, it's what's the shape, okay? So I give you a picture, I just look at it, I can tell you what's the shape. The astronomers can easily do that. So this can be done reliably by human expert. However, these days, because of the technology advancements, the Hubble Space Telescope, recently James Webb Telescope, they can send you too much data for human expert to reliably classify it. So you need a better way. Even astronomers, they realized, oh, we cannot keep pace with the incoming data anymore, using human methods anymore. We need something a little bit more advanced. So let's what is this page? Okay. This our long-term goal is like we could reliably analyze all these images. It's going to help us tremendously. Astronomers, they even, I realized they publish catalog of galaxies. That's to us, it's just a book of images. Then there's a label saying this is what image taken from which telescope, which day, things like that. And that's very important for them. But they realize manually classification of galaxy is not possible anymore because of the data, and also is not as accurate as required because the expert is not 100%. Sometimes we got 10 experts, they may have different opinions, right? So there might be a better way to do it. So because so many in pictures, I cannot just hire people to say, hey, do this, classify these images. So they find a clever way. They develop this citizen science, what did they call it? Citizen scientist project. They put their images online. They designed a series of questions to ask normal people, if you are interested in these subjects, go online, click a link, they show you images, they ask you a sequence of questions, you tell them what this image look like. But they have another way at the back end, statistic person, like our professor sitting here, analyzing all the data, then they have a conclusion, consensus, some kind of a consensus saying, oh, majority of people think the image to the left is an elliptical galaxy, the one in the middle is a spiral, the one to the right is two galaxies merging together. So yeah, we need people's help to do this. So in 2007, they launched the first iteration of this Galaxy Zoo project. It was a great success. And they run this Galaxy Zoo project many iterations now. In the first iteration, they only ask the public assistance to classify the image into 3 categories. In the second, what we call Galaxy Zoo number 2, they ask the public to identify the images into 7. Did I say 7? 7 different categories. So it's becoming more and more complex or more and more interesting. So as I said, they give you a decision tree like interface. You go to the first image, they ask you, is this galaxy smooth or rounded with no sign of a disk? Depending on what you answer, they lead you to the next question. There's a sequence of questions, as you can see here. And they collect all this data in a big Excel sheet, sometimes with missing data. Okay, that's what they do. Eh? With all this data, the machine learning people may come to help a little bit to see what we can do. Before deep learning these days, everyone is talking about deep learning, but before deep learning, machine learning is already there. There are some traditional machine learning classification algorithms, such as shown here, maybe decision tree, well known SVM is also well known as well. So these days we got deep learning, neural network stuff. So there was a comparative study recently was done by a PhD student, I think in Brazil. They compared the traditional machine learning methods with the more state-of-the-art CNN-based machine learning algorithm to see which one is better. It comes to the conclusion that the more recent neural network-based machine learning method is a little bit better than the traditional ones. And in this work, we kind of look at all the different studies that have been done, and we choose a ResNet, a residual network, to do the classification job. So that's kind of the background. And if I move forward, which I will skip a few slides, this is a very typical introduction to ResNet. It's kind of a special construction of a convolutional neural network, try to solve the problem of vanishing or exploding gradient problem. So I wouldn't go into the details of this slides, but this gives you the idea of the technology we use. And just CNN these days is like everybody knows, it's very good for image classification, computer vision, and all that. And this is just a funny picture of a typical CNN. It just takes too much time writing or explaining this because so many little components, right? Convolution, pooling, sampling, and all that. So I will just skip that as well. Okay, so yeah, as I mentioned, the ResNet, they try to solve the exploding or vanishing gradient descent problem, because when you have a very deep neural network these days, people know deep neural network, and not only neural network has been around since 60s, last century. It was not gaining any traction until maybe 20, 15 years ago. So deep, it's very deep, okay? Many layers, but when you do the back propagation through these many layers, they got the problem of exploding or vanishing gradient, such that the updating of the weights becomes very, very slow, or the whole loss function is not improving, or sometimes even getting worse. So people in 2015, they developed this new idea, residual network, which could solve this problem, such that you can have theoretically thousands of layers of your neural network that you can still train it. It still can give you reasonable result. But typically, people would see ResNet 5.0. It's kind of a popular. There's a 15 layers. That's quite deep already. So ResNet is an important technology we use here. The data set we gathered is from the Kaggle website, which is a very popular website for people doing data science. So I have an original data set. So on the left column in the table, it shows every picture's ID, and we have information of every picture belong to which class. Those little numbers are probabilities. These are the initial original data set. We put original data set. We've got folders. We download all these pictures, the Excel sheets. We know those zeros are not missing data. They just mean the probability 0. It might be a rounding error there, but they say this image is not in this class. So this is our initial data set. And we got a total 61,578 galaxy images that we downloaded. We kind of clean it up a little bit, depending on, we got 2 experiments to carry out. We curated our data set number 1. This is for classifying 5 different galaxy types, morphologies. So these are the name of these different 5 galaxy shape or morphology and the number of samples in those 5 categories. This is our data set number 1. This data set was used in a few research. I think it is mentioned here, and we will do some comparison later on with those research. We also curated another data set from our original Excel sheets. This is with the data set number 2. This is for preparing for the experiment that we're going to do the classification for 7 distinct classes. And this is a table summarize the name of these 7 distinct classes and the number of images in the data set. Okay, so this just gives us an idea of the 5 classes galaxy on top. That is, we're using data set number 1, D1. The bottom is we're classifying 7 different galaxy images, data set 2, D2. Okay, these are the data set we prepared. And the people have done this, not exactly on the same data set, but on this topic of using machine learning or deep learning to help classifying galaxy images. So as you can see, there are different techniques used. In this research paper, they used the D2. They achieved certain metrics here. So we don't have to remember those because I will show a table to summarize all this. So as deep learning technique improves, people try to use a new one to see how it performs these days compared to previous ones. And other research here, another research in reference 21 was performing an experiment on dataset D1, and they achieved some results. Okay, sometimes I only say accuracy, sometimes I say precision or F1 score. That was because the original paper, they only reported that. Okay, so if I move on, so you can see this is typical other papers, a lot of papers, many of them, they're using different techniques to do the classification. Sometimes they use D1, sometimes they use D2, sometimes they use their own data set, which makes the comparison a little bit harder in that case. For example, this reference number 9 is for classifying only 3 classes. That's not what we are doing here. We're doing 5 and 7, but we listed here as a literature review because this was maybe one of the first work in this area. Okay, so let me just quickly maybe go to this table here, showing the first column, showing previous researchers, different papers, what data set they use, what metrics they reported. So you can see sometimes they don't report accuracy, precision, recall, and all that. They only report something. There's something, whatever they reported, we show it here. Okay, so now it comes to, we're going to do it a little bit differently given the recent advance in deep learning architecture. There are better architecture these days than before, so let's see how they perform. So we typically grab an image, we resize it to a reasonable size that we can use. We split the data set D1, D2 in a typical ratio, 9:1 or 8:2, but we choose 9:1. We use some typical data augmentation technique just to increase our data set a little bit. So the typical data augmentation, we use maybe horizontally, vertically flip a little bit, rotate a little bit, things like that. Very typical in machine learning. And this is the data set D1, and it shows how many training images, how many testing images we're going to be using. And just similarly, we have data set 2. This is for 7 classes classification, how many training, how many testing in each category. Okay, and we have our own model, which is a little bit variant of the ResNet. we change it a little bit, such as when we do convolution, we don't do normal convolution, we do separable convolution, because it's computationally better than traditional convolution. Okay, so we just do little changes here and there. These two slides is illustrating that. And okay, I probably should skip this bit. This is talking about what do you mean by convolution. Probably everyone knows these days what is convolution. And the separable convolution layer that we used is for computational consideration, because it's a lot of computation going on there. If you are using traditional conventional convolution operation, it's too much calculation for the little laptop we have. So we choose this separable convolutional operation, which is a little bit recent. It is much laptop friendly, let's say, if you do not have a GPU. Okay, so we do our experiments on both dataset D1 and D2, and we also compare with other popular deep learning architecture that has been used. So as you can show here, as you can see here, and when we do the comparison, we measure precision recall, F1 score accuracy, just very typical for many machine learning tasks. Then we show the little laptop we have, the specification in terms of hardware. Okay, so this typical, very well-known deep learning architecture, you can import it, then you can customize it, such as how many kernels, things like that. You can customize a little bit. So this table shows first, on the bottom, how many parameters you need to have, right? The less parameters supposedly is a little bit cheaper than if you need to billions, such as the ChatGPT guys, billions of parameters, less parameter, less computational demanding. So this just shows maybe we are using a little bit less parameter, we're using separable convolutional and all that. We just want to save power and operations and all that. Typical diagrams that we can get when you are using TensorFlow and all those packages, they show you those diagrams showing your training, your loss, they're getting down, I mean, improving and all that. And confusion matrix and all that typical stuff generated by the program, I mean, by the package. And the last here is the precision recall and F1 score computed by the package, by the program we used. Okay, this shows similar idea that the performance of the typical CNN models, such as VGG16, 19, ResNet 15, Inception, and what their results are. I know it's a lot of too much information, but I will have a summary table later on just to show you what it looks like. And another result, this is on dataset D2. And again, the same kind of information just to show how it performs. Okay, so let me move on. Okay, I would say this summarizes everything that has been done in this work. These are the different studies, and the last row is our study here. What model they use, what data set they were using, and the results. Okay, I only reported the accuracy here. And there's only one other paper we find that we're using dataset D2, and these are their results. Okay. I guess that's what we do and what we have done on this work. And we tried a new ResNet architecture. We made a little bit of change, not too much. We tried it on the data set we obtained, and we'll try to see how it performed compared with other existing work. And it seems it's a little bit better, at least for D1. So that is this work is about. Okay, I guess these are some of the references, and thank you much for your attention. And I will be happy to take any questions you may have. Thank you.